and welcome to this video covering an introduction to the pigeonhole principle. And yes, you're right, the animated bird on the screen is not a pigeon, but it looks nice, doesn't it? Before we look at the formal definition of the theorem, think about this. What is the connection between pigeons entering the pigeonholes and the party game musical chairs? Here we have 6 very happy, perhaps drunk, members of a group engaging in the classic party game of musical chairs. Remember, there is always one chair less than the number of players. The idea is that as the music plays, each person walks around the chairs. As soon as the music stops, each player scrambles to take a seat. Of course, each time there will be one person missing out. Keep this in mind, that there is only one person without a chair each time. Now let's look at our friend the pigeon, after whom the theorem is named. At the bottom are 7 pigeons. Yes, they are pigeons this time. On the right are the pigeonholes to which each of them will fly. Let's see this in action. First one, second, third. Very predictable, isn't it? And one more. Obviously the 7th pigeon missed out because there was one less pigeonhole, just as there was one less chair available in the musical chairs game. Now let's have a look to see where the principle comes from. The pigeonhole principle is also known under 2 other names, the draw principle and the box principle. It was developed by a German mathematician nearly 200 years ago, and his name is Johann Peter Gustav Lejeune Dirichlet. That's a mouthful, isn't it? And he was born in Düren, Germany, which was actually then a French empire of sorts. And his principle is actually very simple. This is what he said. If more than n objects are distributed in n boxes, then there will be at least one box with 2 objects. That's like saying if you've got more things than there are spaces to put them in, there will be some left over. It's stating the obvious, isn't it? But it becomes a very powerful tool in mathematics. In our game of musical chairs, each time we had n plus 1 people and n chairs. That's a way of showing it using algebra. And for our pigeons, there were 7 pigeons but only 6 holes to put them in. Dirichlet developed this principle in relation to some high-level mathematics work involving number theory. However, since this is only going to be an introduction to his principle, we're only going to look at some real-life applications that we can appreciate. And here's the first one, which I've called socks in the dark. Let's start with choosing socks, just like we do each morning. In your sock drawer, let's say, there are identical socks of 3 different colours, as you can see there, which to me look like black, cream and perhaps light green. The light switch doesn't work, so you can't see the socks in the dark. So what you do, you pull out socks at random, one at a time. And the question is, what's the minimum number of socks you must pull out to make sure that you have a pair of socks the same colour? How can we apply the pigeonhole principle to this situation? Well, let's have a go. Let n be the number of socks we take out of the drawer. We know there are 3 different colours to choose from. What we want for the minimum number is to have the last sock that we take out to be the same colour as one of the other socks already taken out. And we can show this like the following. If we divide the number of socks we have to take out by 3, the remainder has to be 1. And that would be the sock that has the second colour the same. And you can see that the numbers that make this work will be 4, 7, 10, 13 and so on. Because each of them, when you divide by 3, leave a remainder of 1. There we are. Now, of course, we're looking for the minimum. So what can the number n be? It must be 4. That means we must choose a minimum of 4 socks to ensure that at least 2 of them are the same colour. And we can show all the combinations as you can see there. In the first situation we can take out one of each colour and the fourth sock will be black. In the second situation, one of each colour and the fourth sock will be cream, or in the last combination, one of each colour and the fourth sock will be green. In either case, we need a minimum of 4 socks. Okay, let's try another one. Happy birthday. I don't know if you've noticed, but the best way of approaching these sort of problems is to think of the worst possible case when you are working out how many you need to take out or how many things you need to do. For this problem, it's your birthday and you want to randomly invite friends so that at least one of them was born on the same day of the year as yourself. Perhaps your birthday was July 1st. So that means how many friends should you invite so that at least one of them shares the same birthday as you, July the 1st. In these situations, always think of the worst possible case. That means the maximum number you need to choose from, which might give you what you need. It sounds a bit contradictory, doesn't it? We know there are 365 days in a year, or 366 for a leap year. So that means if you invite 364 friends that do not share your birthday, and each one of them has a different birthday, and that's the worst possible case, isn't it? That's the maximum. And that means when you invite one more person, in other words, 365 friends, that person must share your birthday because all of the other birthdays have been covered. Obviously, for a leap year, it will be one more each time. Okay, let's finish by doing one more called the animal farm. So we are visiting our animal friends on the farm. As you can see, there are 20 goats, chickens, and pigs. And this is what's happened. 8 of our animals, for some reason, have escaped. Can we show or prove that at least 3 of those escapees are of the same type? That means at least 3 of them are either goats, chickens, or pigs. Again, let's begin by thinking of the worst possible case. And that means that out of the 8 that have escaped, the first 3 will be different animals, and then the second lot of 3 will also be different, and the last 2 will be different as well. And the combinations for that will look like the following. There they are. First combination, the first 3 are different, the second 3 are different, and the last 2, let's say, are a goat and a chicken. Or the second combination will be that the last 2 are a goat and a pig. Or the final one, that the last 2 are a chicken and a pig. In each case, you can see that we have at least 3 of each animal. In the first combination, we have 3 goats and 3 chickens. In the second combination, 3 goats and 3 pigs, and in the third combination, 3 chickens and 3 pigs. And we can show this, of course, another way using the Pigeonhole Principle. There are 8 animals that have escaped, and we want at least 3 of them to be the same. So let's divide 8 by 3, which is approximately 2.7. That means approximately 2.7 animals will be the same. Of course, we can't have 0.7 of an animal, so we can round that up to 3 animals, which is what we showed using our diagrams. So I hope that this introduction to the Pigeonhole Principle gave you some idea about what it's all about and its usefulness in real-life context. I look forward to your company in my next video. Bye for now.